Hello there, and welcome back to the Sleepy Ocean. Tonight, we are going to embark on a voyage of acoustic discovery, stripping away the opaque blue curtain of the water to reveal the hidden topography of our planet, using the power of sound. We are delving into the world of ocean sonar mapping. To begin, we must first confront the sheer, overwhelming invisibility of the sea floor. For most of human history, the ocean bottom was a place of conjecture and myth, a plumbless void that swallowed ships and anchors into an eternal unknown. Unlike the land, which we can survey with our eyes and measure with our strides, the seabed is hidden beneath a medium that blocks light almost instantly. Sunlight, the primary tool of terrestrial cartography, is absorbed within the first few hundred meters of the water column. Beyond that, the ocean is a realm of absolute darkness. Consequently, we cannot map the ocean by looking at it. We must map it by listening to it. We have to shout into the abyss and wait for the abyss to shout back. This process transforms the physical landscape of mountains, canyons, and plains into a landscape of time. The time it takes for a sound wave to travel down, touch the bottom, and return to the surface. It is a slow, rhythmic process of revelation, where we paint the world in the dark, using pulses of noise, turning the silence of the deep into a detailed portrait of the Earth's crust. Before the invention of the electronic ping, the only way to touch the bottom was with the lead line, a tool of immense simplicity and back-breaking labor that defined maritime sounding for thousands of years. A lead line consists of a heavy lead weight, usually shaped like a slender cone or a hexagonal prism, attached to a thick hemp rope. The base of the lead weight was often hollowed out and filled with tallow, animal fat. This arming the lead allowed the sailor to bring up a physical sample of the bottom. If the tallow came up with sand, the bottom was sandy. If it came up with mud or crushed shells, the captain knew where he was. Mapping a coastline with a lead line was an exercise in brute force. A sailor stood in the chains, a platform on the side of the ship, and swung the lead weight in a great vertical circle, releasing it to fly forward and sink as the ship moved. He would feel the line go slack when it hit the bottom and read the depth by the marks, leather or cloth tags, and deeps, unmarked sections, on the rope. This method was slow, providing only a single point of data at a time, a pinprick of knowledge in a vast ocean of ignorance, requiring the ship to slow down or stop for every measurement, making the mapping of the deep ocean practically impossible. The challenge of deep sounding with a rope in the open ocean was a logistical nightmare that occupied the great explorers of the 19th century. When Sir James Clark Ross attempted to sound the abyssal plains of the Atlantic in 1840, the process took hours. As the lead weight descended thousands of fathoms, the weight of the rope itself became heavier than the lead. It became difficult to tell when the lead had actually hit the bottom because the rope would keep unspooling under its own weight. Furthermore, deep currents would drag the line into a massive curve, distorting the measurement. A single deep-sea sounding required the ship to hold a perfect position for half a day, while the crew laboriously hauled miles of wet, heavy hemp back onto the deck. Because of this extreme difficulty, by the late 19th century, humanity had fewer than 200 reliable soundings for the entire deep ocean. We knew more about the surface of the moon through telescopes than we did about the geography of the Atlantic floor, which remained a featureless blank on the maps, interrupted only by the occasional, hard-won number scribbled in the blue. The father of modern oceanography, Matthew Fontaine Maury, was the first to attempt to collate these sparse data points into a coherent picture of the seafloor. Working in the mid-19th century, Maury was a US Navy officer who analyzed thousands of ships' logs. He realized that by combining the few deep soundings available, he could infer the shape of the basin. He famously identified the Telegraph Plateau, a relatively shallow region in the North Atlantic that we now know as part of the Mid-Atlantic Ridge. Maury's work was a triumph of data aggregation before computers existed. He visualized the seabed not as a bottomless pit, but as a terrain with hills and valleys, covered in a downy layer of microscopic shells. His map was the first to suggest that the ocean floor was a continuous landscape, a physical bridge of geology connecting the continents, waiting for a cable to be laid across its spine. Maury proved that the deep was accessible, provided one had the patience to lower a wire and the intellect to interpret the tension. The catalyst that finally drove humanity to invent a faster way to see through water was the tragedy of the RMS Titanic in 1912. The sinking of the unsinkable ship by an iceberg, a silent, submerged hazard, shocked the world and created an immediate demand for a device that could detect underwater objects ahead of a vessel. The tragedy highlighted the failure of visual lookouts. Inventors scrambled to find a solution. One such inventor was Reginald Fessenden, a Canadian radio pioneer. In 1914, just 2 years after the disaster, Fessenden tested his oscillator in Boston Harbor. This device was a massive electromagnetic shaker that produced a low-frequency hum. Fessenden lowered it into the water and successfully bounced a sound signal off an iceberg miles away, receiving an echo. He also bounced a signal off the sea floor. This was the birth of the echo sounder. It was the first time an electronic voice had called out to the bottom of the world and received an answer, proving that sound could do what light could not. Travel through the heavy, dark water to find the solid threats hidden within. To map with sound, one must understand the medium, and the speed of sound in seawater is a variable beast, not a constant. On average, sound travels at 1,500 meters per second in the ocean, more than 4 times faster than it travels in air. This high speed makes the ocean an incredibly efficient conductor of acoustic energy. However, this speed, denoted as c, fluctuates based on 3 primary factors: temperature, salinity, and pressure. Sound travels faster in warm water, faster in salty water, and faster in deep water due to pressure. As a sonar pulse travels down into the abyss, it moves through layers of water with different properties. It might speed up as it passes through a warm surface layer, slow down as it enters the cold thermocline, and speed up again as the pressure mounts in the deep. These changes cause the sound waves to bend or refract, much like light passing through a lens. A sonar operator must account for these curves. Otherwise, the map will be distorted. We are essentially trying to measure a straight line using a ruler that bends as we push it deeper into the water. The piezoelectric effect is the physical phenomenon that makes modern sonar possible, transforming electricity into rock-crushing vibration. It was discovered by Pierre Curie and his brother Jacques in 1880, but applied to sonar by Paul Langevin during World War I. They found that certain crystals, like quartz, deform physically when an electric voltage is applied to them. Conversely, if you squeeze the crystal, it generates a spark. In a sonar transducer, a ceramic material, modern versions often use lead zirconate titanate, is subjected to a rapid electrical pulse. The crystal expands and contracts thousands of times per second, vibrating against the water face. This vibration creates a pressure wave, the ping. When the echo returns from the seafloor, the faint pressure of the sound wave hits the ceramic, compressing it slightly and generating a tiny electrical signal that the computer reads. The heart of the sonar is a breathing crystal, a stone that sings when shocked and listens when touched by the ghost of its own voice. Deep in the ocean, there exists a specific layer known as the SOFAR channel, sound fixing and ranging, or the deep sound channel, which acts as a planetary scale speaking tube. This channel usually sits at a depth of around 1,000 meters, where the opposing effects of temperature and pressure create a zone of minimum sound speed. Sound waves trapped in this channel are constantly refracted back toward the center of the layer, preventing them from scattering at the surface or being absorbed by the bottom. Because the energy is focused, sound can travel for thousands of miles within this channel with very little loss. A small explosive charge detonated in the SOFAR channel off Australia can be heard by listening stations in Bermuda. Whales have used this channel for millions of years to communicate across ocean basins. For mappers and military subs, it is a highway of noise, a layer of the ocean where the acoustics are so perfect that the world becomes a small, echoing room. The first generation of echo sounders were single-beam systems, effectively acting like a flashlight pointing straight down into the dark. The ship would transmit a single pulse directly beneath the keel, measure the time it took to return, and record a single depth point. As the ship steamed forward, it created a line of depth points, a 2D profile of the sea floor directly under the ship. While this was a massive improvement over the lead line, it left huge gaps. The ship could sail right over a mountain peak, located just 100 meters to the port or starboard, and miss it entirely. Mapping the ocean with a single beam was like trying to map a continent by walking across it in the dark with a laser pointer aimed at your feet. You would know the elevation of your path perfectly, but you would remain oblivious to the Grand Canyon lurking just to your left. This limitation meant that early bathymetric maps were filled with interpolation, guesses, drawing smooth planes between the known lines where, in reality, rugged chaos existed. During the Second World War, the urgent hunt for submarines revealed a mysterious phenomenon known as the Deep Scattering Layer, DSL, or the phantom bottom. Sonar operators would often detect a solid reflection at a depth of 300 to 400 meters during the day. This false bottom would rise to the surface at night and sink again at dawn. It was baffling. The seafloor should not move. Eventually, biologists realized this layer was composed of billions of biological organisms, lanternfish, siphonophores, and krill, migrating vertically. Their swim bladders and bodies were dense enough to reflect the sonar ping. This discovery was a nuisance for mappers, who had to tune their instruments to punch through this living cloud to see the real bottom. But it revealed the sheer density of life in the mesopelagic zone. The ocean floor was hidden not just by water, but by a false floor made of living meat that moved with the sun. The acoustic impedance of the seabed determines how loud the echo will be, allowing sonar not just to measure depth, but to determine what the bottom is made of. Acoustic impedance is the product of the density of the material and the speed of sound within it. When a sound wave hits a boundary between two materials with very different impedances, like water and granite, most of the energy is reflected, creating a strong, sharp echo. When it hits a boundary with similar impedance, like water and soft, fluffy mud, much of the sound is absorbed or continues into the sediment, creating a weak, fuzzy echo. By analyzing the backscatter intensity, scientists can paint a geological map. A bright, loud return means rock, coral, or shipwreck iron. A dark, quiet return means mud or silt. We can feel the texture of the bottom without touching it, distinguishing between a safe, sandy anchorage and a jagged, rock-strewn trap simply by the quality of the shout that comes back. The development of side-scan sonar revolutionized our ability to see the texture and debris of the seafloor by changing the angle of the view. Instead of looking straight down, a side-scan towfish is dragged behind the ship near the bottom, emitting fan-shaped pulses to the left and right. These pulses skim across the seabed at a low angle, casting acoustic shadows. Just as the setting sun elongates the shadows of trees, revealing the topography of a landscape, the side-scan sonar uses sound to create shadows behind rocks, wrecks, and ripples. A tall shipwreck casts a long acoustic shadow where no sound returns. The resulting image looks like a black and white photograph. It doesn't measure depth directly, but it reveals the roughness of the world. It allows us to see the rivet patterns on a sunken boiler or the scour marks of a trawler net, painting a picture of the seabed that is defined by the absence of sound in the shadow zones. The discovery of the Mid-Atlantic Ridge, the immense mountain range that bisects the ocean, was largely the work of Marie Tharp, a geologist who mapped the ocean from a basement office at Columbia University. In the 1950s, women were not allowed on research vessels, so Tharp worked with the sonar profiles brought back by her colleague Bruce Heason. As she aligned the single-beam profiles, she noticed a recurring feature: a deep notch in the center of the ridge. She realized this was a rift valley, a place where the Earth was pulling apart. This was the smoking gun for the theory of plate tectonics and continental drift, which was still controversial at the time. Tharp literally drew the seam of the world. She used her pen to connect the sounding dots, revealing that the ocean floor was not a flat, ancient plain, but a dynamic, spreading factory of new crust. Her map, drawn from the echoes of isolated pings, changed our understanding of the planet's geology forever. The ping itself is not a simple noise. It is a carefully engineered packet of energy known as a pulse. In modern sonar, the duration and frequency of this pulse are critical. A short pulse provides better vertical resolution. You can distinguish two objects close together, but it has less energy and can't travel as deep. A long pulse carries more energy for deep mapping, but blurs the detail. To solve this, modern systems use a chirp, or frequency-modulated FM, pulse. The sonar sweeps through a range of frequencies within a single ping, sliding from low to high notes. This chirp allows the system to put a lot of energy into the water while retaining the ability to process the return signal with incredible precision. It is the difference between banging a drum and singing a sliding scale. The chirp carries a signature that allows the computer to pick it out from the background noise of the ocean, identifying the exact moment the bottom replied. The transducer is the ceramic heart of the sonar system, a device that must withstand the violence of its own operation. When a high-power deep-water sonar fires, the voltage across the ceramics can be thousands of volts. The physical expansion of the crystals creates a pressure wave that can be loud enough to boil the water on the face of the transducer, a phenomenon called cavitation. If the water boils, the bubbles block the sound and can damage the equipment. Therefore, sonar engineers must carefully design the system to pulse just below the threshold of cavitation. The transducer is often housed in a blister or a gondola on the hull of the ship, streamlined to reduce the noise of water rushing past. It is a sensitive ear, encased in a tough hydrodynamic shell, listening for a whisper from 5 miles down while enduring the thundering flow of the ship's passage through the waves. Attenuation is the relentless enemy of the sonar signal, the absorption of sound energy by the water itself. As a sound wave travels, its energy is converted into heat due to the viscosity of the water and chemical relaxation processes involving magnesium sulfate and boric acid molecules. High-frequency sounds, high pitch, are absorbed very quickly. A 100 kHz signal might only travel a few hundred meters before fading away. Low-frequency sounds, low pitch like a bass drum, travel much further with less loss. This creates a fundamental trade-off. To map the deepest trenches, 11,000 meters, we must use low frequencies, to 12 kHz. which have long wavelengths and lower resolution. To map a shipwreck in shallow water with photographic detail, we use high frequencies, 500 kHz, but we must be right on top of it. We cannot have both range and resolution. The physics of the water molecule demands a sacrifice of detail for every mile of depth we wish to reach. The correction for the ship's motion is a mathematical feat that keeps the map steady while the platform heaves, pitches, and rolls in the ocean swell. A research vessel is a terrible place to measure distance from. It is constantly moving in 6 degrees of freedom. If the ship rolls to the left just as the sonar pings, the sound beam shoots off to the side instead of straight down. If the ship heaves up on a wave, the depth reading will be artificially long. To fix this, modern survey ships are equipped with an inertial motion unit, IMU, a high-precision sensor package containing gyroscopes and accelerometers. This unit measures the ship's attitude hundreds of times per second. The sonar computer takes this data and electronically steers the sound beams to compensate, keeping them locked vertically on the seafloor even as the ship wallows in a storm. It is like trying to use a sniper rifle while riding a bucking bronco, relying on a computer to pull the trigger at the exact split second the barrel is level. The footprint of the sonar beam determines the resolution of the map, defining how small an object we can see. As the sound cone travels downward, it spreads out. In deep water, a single beam might illuminate a patch of the seafloor hundreds of meters wide. The sonar returns a single average depth for that entire patch. This means that in the deep ocean, using surface ship sonar, we cannot see objects smaller than a football stadium. A car, a shipping container, or a small plane wreck is invisible, lost in the pixel size of the beam. To map smaller features, we must get the sonar closer to the bottom, towing it on a cable or mounting it on a submarine. This geometrical spreading is why we have better maps of Mars than we do of the deep Pacific. There is no water in space to spread the radar beams, but the ocean forces us to look through a widening fog of sound that blurs the details of the deep. The discovery of hydrothermal vents in 1977 was a triumph of sonar anomalies and temperature spikes. Sonar operators mapping the Galapagos Rift noticed slightly fuzzy returns and temperature anomalies near the bottom. When they sent the submersible Alvin down to investigate, they didn't find just rocks. They found towering chimneys of black smoke and ecosystems fueled by chemosynthesis. The sonar had detected the density difference of the hot, mineral-rich water pluming out of the vents. These black smokers were invisible to the naked eye from the surface, but their acoustic signature, a subtle shimmering in the sound return caused by the turbulence and temperature gradient, gave them away. Sonar allowed us to find the heat leaks of the planet, leading to the discovery of life forms that exist entirely independently of the sun. Finally, for this first descent into the science of sounding, we must consider the sheer emptiness of the data we currently possess. Despite all our technology, less than 25% of the ocean floor has been mapped with modern, high-resolution sonar. The vast majority of the blue areas on Google Earth are not real data. They are predicted depths based on satellite gravity readings. Satellites can sense the slight bulge of the ocean surface caused by the gravitational pull of massive underwater mountains. This gives us a blurry, gravity-based estimation of the seafloor, but it is not a map. It misses anything smaller than a few kilometers across. When a ship actually runs a sonar line through these predicted areas, it often finds seamounts, canyons, and faults that were completely unknown. We are still driving blindly through most of the ocean, relying on a gravity sketch to navigate a landscape that is as complex and rugged as the Rocky Mountains, hidden beneath the eternal crushing weight of the sleepy ocean. The revolution of multibeam echo sounding marked the transition from acoustic blindness to panoramic vision, transforming the survey ship from a vessel dragging a single line of sight into a platform capable of painting a massive swath of the sea floor in a single pass. While the older single-beam systems acted like a blind man, tapping a cane directly in front of his feet, the multibeam system acts like a floodlight. A specialized transducer array mounted on the hull transmits a fan-shaped pulse of sound that spreads out perpendicular to the ship's path. This fan can be several times wider than the water depth, illuminating a broad strip of the seabed known as the swath. The receiver is not a single ear, but a complex array of hundreds of individual listening elements. Through a process called beamforming, the onboard computer electronically steers the listening focus to hundreds of distinct angles simultaneously. It measures the time of return for each angle, creating hundreds of depth points in a fraction of a second. As the ship moves forward, this fan of sound sweeps along the bottom like a broom, building a continuous three-dimensional ribbon of topography. This technology allows a ship to map a mountain range as wide as the Alps in a matter of weeks, capturing the grandeur of the underwater landscape with a density of data that reveals faults, craters, and dunes that were previously hidden in the gaps between the single lines. The distinction between bathymetry and backscatter imagery is the difference between feeling the shape of an object and seeing its texture. Bathymetry measures the time of flight, how long the ping takes to return, which tells us the depth and topography. It gives us the geometry of the seafloor. Backscatter, however, measures the intensity of the return, how loud the echo is. This tells us what the bottom is made of. A hard, jagged basalt lava flow reflects sound violently, sending a deafening echo back to the ship. A soft, thick layer of pelagic ooze or mud absorbs the sound, returning a whisper. By mapping these intensities, scientists create a mosaic that looks like a black and white photograph. Darker areas might represent soft sediment, while lighter, brighter areas represent hard rock or shipwreck iron. This acoustic texture mapping allows geologists to identify potential habitats for deep-sea corals, which prefer hard rock, or to spot the debris fields of ancient landslides that are indistinguishable from the surrounding mud by depth alone, but stand out starkly in the acoustic reflection. To map accurately, the hydrographer must constantly battle the bending of sound caused by the ocean's thermal structure, a task that requires the deployment of the CTD, conductivity, temperature, and depth probe. The ocean is not a uniform block of water. It is a layered cake of varying temperatures and salinities. Sunlight warms the surface, creating a mixed layer. Below this lies the thermocline, where temperature drops rapidly with depth. In the deep abyss, the water is uniformly cold and pressurized. Each of these layers has a different sound velocity. If the sonar computer assumes a constant speed, the map will be warped. A smiling seafloor artifact occurs when the sound speed used is slower than reality, causing the edges of the swath to curl upward. A frowning artifact occurs when the speed is too fast. To correct this, the ship must stop and lower the CTD cage on a wire, often to the very bottom. As it descends, it profiles the water column. This data is fed into the sonar processor to correct the refraction of the beams. It is a tedious, repetitive ritual of dipping a thermometer into the abyss to ensure that the mountains on the map are actually where we think they are. Exploring the history buried beneath the sediment requires a different kind of acoustic tool, known as the sub-bottom profiler, or chirp sonar. While multibeam sonar reflects off the surface of the sea floor, the sub-bottom profiler uses a much lower frequency pulse that penetrates the mud. It ignores the boundary between water and sand and continues downward, reflecting off the layers of sediment, rock, and buried debris below. This device produces a cross-sectional image that looks like a slice of layer cake. It reveals the stratigraphy of the ocean floor. Archaeologists use it to find ancient riverbeds that were drowned by rising sea levels at the end of the Ice Age, or to spot ships that have been completely buried by shifting sands. Geologists use it to trace the history of earthquakes by looking for displaced layers of sediment. It is a geological X-ray machine, peeling back the skin of the seafloor to show the skeleton of the earth underneath, revealing a history of deposition and erosion that has been sealed in the dark for millions of years. The cutting edge of underwater mapping is synthetic aperture sonar, SAS, a technology borrowed from radar that defies the physical limits of traditional resolution. In standard sonar, the resolution is limited by the size of the transducer. To get a sharper image, you need a bigger antenna. But underwater vehicles are small. SAS solves this by using the forward motion of the vehicle to synthesize a virtual antenna that is hundreds of meters long. As the autonomous underwater vehicle, AUV, swims along a straight line, it pings the same spot on the seafloor multiple times from slightly different positions. The computer stitches these echoes together, mathematically simulating a receiver array that spans the entire distance the vehicle traveled. This allows for pixel-perfect resolution that is independent of range. A SAS system can spot a coin on the seafloor from hundreds of meters away. It produces images of such clarity that they look like optical photographs, revealing the individual links of an anchor chain or the scour marks of a crab, turning the murky acoustic world into a realm of high-definition precision. The geometry of the multi-beam swath creates an inevitable dead zone, or nadir gap, directly beneath the ship in side-scan systems, though modern multi-beam systems have largely solved this. In traditional side-scan sonar, the transducers look out to the sides, leaving a blind spot directly under the towfish. The pulses travel horizontally, grazing the bottom. This creates beautiful shadows that highlight texture, but it misses the ground zero. To fill this gap, surveyors must run overlapping lines, stitching the edges of one pass to the center of the next. This mowing the lawn pattern requires precise navigation. The ship drives back and forth in parallel lines for days or weeks, ensuring that every square meter of the bottom is insonified from at least 2 angles. It is a test of endurance and boredom, a slow, methodical erasing of the white space on the chart, driven by the obsessive need for complete coverage. Mapping the continental shelf presents a unique set of challenges compared to the deep ocean, primarily due to the interference of tides and the sheer volume of data required. In shallow water, the footprint of the sonar beam is very small. A ship in 10 meters of water might only map a strip 30 meters wide. To map a large bay, the ship must drive thousands of track lines back and forth. Furthermore, the tide is constantly raising and lowering the sea level. A depth measured at high tide will be different from one measured at low tide. Hydrographers must install tide gauges on the shore to record the water level every few minutes, and then mathematically subtract the tide from the sonar data to create a consistent map relative to a fixed datum. The shallow water is also noisy, filled with the sound of breaking waves, ship traffic, and shifting sands. It is a high-effort, low-yield environment where the map is built inch by inch against the constant fluctuation of the sea surface. The acoustic evidence of past ice ages is written on the seafloor in the form of massive glacial scour marks, which are clearly visible in high-resolution sonar data. On the continental shelves of Antarctica, Greenland, and even the North Sea, sonar reveals deep, parallel gouges running for miles. These are the tracks of massive icebergs that grounded on the seabed thousands of years ago. As the icebergs drifted, their keels plowed through the sediment, pushing up berms of mud on either side. These plow marks can be tens of meters deep and hundreds of meters wide. They crisscross the seabed like the tracks of giant tanks. In deeper water, we see mega-scale glacial lineations, streamlined ridges formed by the fast-flowing ice streams of ancient ice sheets. These acoustic scars allow glaciologists to reconstruct the flow and retreat of the ice caps, proving that the glaciers once extended far out onto the continental shelf, grinding the earth beneath them as they marched into the sea. The Storegga slide off the coast of Norway is one of the largest underwater landslides in history, and its anatomy has been revealed in terrifying detail by sonar mapping. About 8,000 years ago, a massive section of the continental shelf collapsed, sending 3,000 cubic kilometers of sediment sliding into the deep Norwegian Sea. The sonar map shows the headwall of the slide, a steep underwater cliff hundreds of kilometers long where the shelf broke away. Below this cliff lies the chaotic debris field, a jumbled landscape of massive blocks of rock and mud that flowed like a liquid avalanche for hundreds of miles. This event generated a tsunami that devastated the coastlines of the North Atlantic. The sonar imagery allows scientists to model the physics of the collapse, identifying the weak layers of clay that failed. It is a forensic scene of a geological catastrophe, a frozen snapshot of the moment the edge of the continent fell into the abyss. Seamounts, the submerged volcanoes that dot the ocean basins, are the focal points of deep-sea mapping because they act as oases of life and hazards to navigation. A seamount is defined as a mountain rising at least 1,000 meters from the sea floor, but not reaching the surface. Sonar reveals them as perfect cones or complex, star-shaped ridges formed by rift zones. Many seamounts are guyots, flat-topped mountains. These were once islands that were eroded flat by waves and then sank below the surface due to the cooling and contraction of the oceanic crust. The sonar profile of a guyot shows a perfectly flat plateau suspended in the deep, often capped with drowned coral reefs. These structures interrupt deep ocean currents, forcing nutrient-rich water toward the surface. Sonar maps help fishermen and biologists locate these upwelling zones, which are teeming with tuna, sharks, and deep-sea corals. They are the invisible islands of the deep, mapped only by the deflection of sound waves against their basalt slopes. The standards for hydrographic surveying are set by the International Hydrographic Organization, IHO, specifically a document known as S44, which dictates exactly how accurate a map must be to be considered safe for navigation. For special order surveys in harbors and channels where underkeel clearance is critical, the hydrographer must prove that they have detected every object larger than 1 cubic meter. This requires 100% bottom coverage, meaning there are no gaps between the sonar beams. The surveyor must demonstrate that the uncertainty of the depth measurement is within a few centimeters. This rigorous standard turns mapping into a legal and safety-critical exercise. A missed rock in a shipping channel can tear the hull of a supertanker. The sonar operator is not just making a pretty picture, they are certifying the safety of the road, proving with statistical certainty that the path is clear for the deep draft vessels that power the global economy. The phenomenon of the ghost echo, or false return, is a constant specter in sonar operations, often caused by the density difference between water layers or biological swarms. A sharp thermocline, the boundary between warm surface water and cold deep water, can reflect sound so effectively that it looks like a solid bottom on the screen. Early sailors sometimes charted these phantom shoals and even gave them names, only to have later ships sail right through them. Dense schools of fish or krill can also create a solid-looking return. Modern multibeam systems have advanced filters to distinguish between the hard return of rock and the fuzzy return of water or biology, but the operator must always be vigilant. The ocean is full of illusions, layers of density that try to trick the sound into reporting a bottom where none exists, requiring a skeptical eye to separate the land from the liquid mirage. Mapping a shipwreck with high-resolution sonar transforms a tragedy into a forensic model, revealing the layout of the debris field in a way that divers never could. A side-scan sonar image of a wreck often looks like a ghostly X-ray. The hard metal of the hull reflects a bright white signal, while the acoustic shadow cast by the ship creates a long, black silhouette on the seabed. This shadow is often more detailed than the reflection itself, showing the profile of the masts, the stack, and even the railings. By analyzing the debris field, the scatter of coal, plates, and luggage, archaeologists can reconstruct the breakup of the ship. Was it an explosion? Did it break in two at the surface? The distribution of the acoustic targets tells the story of the sinking. The sonar sees the ship as a disruption in the texture of the sea floor, a hard, geometric anomaly resting in the organic chaos of the sediment. The search for Malaysia Airlines Flight 370, MH370, in the southern Indian Ocean was the largest and most expensive underwater search in history, resulting in the mapping of over 120,000 square kilometers of previously unknown seafloor. The search area was in a remote, rugged part of the ocean that had never been surveyed. The sonar ships revealed a landscape of extreme complexity. Massive underwater volcanoes, deep rift valleys, and submarine landslides that rival the Grand Canyon. The search did not find the plane, but it produced a map of the abyss that is more detailed than any other deep ocean region on Earth. The data revealed a fracture zone where the Earth's crust had been torn apart. This tragic effort highlighted the vastness of our ignorance. We had to map a mountain range just to look for a needle in a haystack, proving that we know the surface of Mars better than our own ocean floor. The Ring of Fire, the trenches and subduction zones of the Pacific, presents the ultimate challenge for sonar mapping due to the extreme depth. Mapping the Mariana Trench, the deepest point on Earth at nearly 11,000 meters, pushes sonar technology to its breaking point. At this depth, the footprint of a surface-based sonar beam is enormous, reducing resolution. To get better maps, scientists must send AUVs, or towed arrays, down into the trench. These instruments must withstand pressures of 8 tons per square inch. The acoustic signal takes 14 seconds to travel round trip. Mapping the trench reveals the step faulting of the subduction zone, where the Pacific plate is bending and cracking as it dives under the Mariana plate. The sonar shows the jagged scars of this tectonic collision, a slow-motion car crash of continents that is consuming the ocean floor and recycling it into the mantle. Backscatter mosaics allow scientists to perform remote sensing of the seabed geology, classifying sediment types without ever taking a physical sample. By analyzing the angular response of the backscatter, how the sound intensity changes as the angle of the beam changes, algorithms can distinguish between different types of roughness. A gravel bed scatters sound in all directions. A smooth sand sheet reflects it like a mirror, specular reflection. A mud field absorbs it. By calibrating these responses, computers can paint a map where red is rock, yellow is sand, and blue is mud. This allows for habitat mapping on a massive scale. We can map the extent of a scallop fishery or a delicate sponge reef from the surface, managing marine resources by listening to the texture of their home. The detection of gas plumes in the water column is a relatively new capability of modern multibeam systems, allowing us to map the breadth of the planet. Methane seeps and hydrothermal vents release bubbles of gas into the water. These bubbles are strong acoustic reflectors. In the past, sonar operators filtered this noise out to see the bottom. Now, they tune the system to see the water column. The result is a 3D image of towering flares of gas rising from the sea floor, looking like underwater smokestacks. Mapping these seeps is crucial for understanding the ocean's carbon cycle. and finding chemosynthetic communities that live on the methane. The sonar reveals a dynamic seafloor that is leaking energy, spotting the invisible plumes that connect the geology of the crust to the chemistry of the ocean. The nadir problem in side-scan sonar is a result of the geometry of looking sideways. You cannot see what is directly beneath you because the angle of incidence is perpendicular. The sound wave hits the mud and bounces straight back up, providing no shadow and very little textural information. This creates a blind stripe, or a gap in the data right down the center of the track line. To fix this, survey lines are planned with significant overlap, usually 100% or 200%. The ship drives a line and then drives a parallel line offset so that the side scan looks at the ground that was previously in the nadir of the first line. This weaving pattern ensures that every patch of ground is illuminated from the side, casting shadows that reveal the true shape of objects. It creates a redundancy that guarantees nothing can hide in the blind spot of the machine. The rise of autonomous surface vehicles, ASVs, like the sail drone, is transforming ocean mapping into a persistent, low-carbon endeavor. These uncrewed wind and solar-powered boats can stay at sea for months, silently collecting sonar data without a human on board. They move slowly, which is good for data quality, and they are quiet, which reduces interference with the sonar. Fleets of these robot boats are being deployed to map the remote, boring, and dangerous parts of the ocean, the Southern Ocean, the Central Pacific gyres. They are the Roombas of the sea, tirelessly mowing the lawn of the global ocean, beaming data back via satellite, slowly filling in the blank spots on the map, while the human operators sleep in their beds on land. The General Bathymetric Chart of the Oceans, GEBCO, and the Seabed 2030 project represent the grand ambition to have a complete, high-resolution map of the entire global ocean floor by the year 2030. Currently, only about 20–25% of the ocean is mapped to modern standards. The project relies on crowdsourcing data from research vessels, fishing boats, and even super yachts. Every ship with a sonar is a potential mapper. The goal is to end the era of estimation and replace the blurry, gravity-predicted maps with hard acoustic data. This project is the modern equivalent of the Library of Alexandria for the ocean, a repository of depth that will serve as the baseline for understanding climate change, tsunami propagation, and deep-sea biodiversity for the next century. It is the final closing of the frontier, the digital enclosure of the blue planet. The separation of the sonar sensor from the heaving, noisy hull of the surface ship is a critical step in achieving high-resolution imagery, leading to the development of the towfish, a hydrodynamic body dragged miles behind the vessel on an armored cable. When a sonar transducer is mounted on the hull, it is subjected to the violent aeration of the bow wave, the vibration of the engine, and the rhythmic pitching of the ship in the swell. To escape this chaotic environment, hydrographers deploy the towfish. This instrument looks like a torpedo with wings. It is lowered through the water column until it is flying just a few dozen meters above the seafloor, deep in the silent, calm abyss. The cable connecting it to the ship, known as the tow cable, acts as both a leash and a data highway. This cable can be several kilometers long. As it drags through the water, it forms a complex curve known as a catenary. The physics of towing are non-trivial. The ship captain must account for the layback, the immense horizontal distance between the GPS antenna on the ship and the sonar fish far behind and below. If the ship stops suddenly, the heavy fish will plummet into the mud. If the ship turns too sharply, the fish will sink or swing wildly. The towfish effectively decouples the sensor from the weather, allowing it to glide smoothly over the terrain like a low-flying aircraft, capturing acoustic shadows that are long, dramatic, and incredibly detailed because of the low angle of incidence, turning a blurry map into a sharp, textured landscape. The cutting-edge technology of interferometric synthetic aperture sonar, InSAS, combines two powerful acoustic principles to create 3D models of the seafloor with a resolution that rivals optical photography. Standard sonar measures the time of flight to get range. Interferometry adds a new dimension by measuring the phase difference of the sound wave arriving at two slightly separated receiver rows. By calculating the tiny difference in the timing of the wave crests hitting the top row versus the bottom row of sensors, the computer can determine the precise angle from which the echo originated. When combined with the synthetic aperture technique, which synthesizes a long virtual antenna by moving the vehicle, InSAS creates a map where every pixel has a precise 3D coordinate. This technology corrects for the layover effect, where tall objects appear to lean over in traditional side-scan imagery. Instead of a flat picture, InSAS produces a true digital elevation model of the seabed debris. We can see the scour pits around individual rocks, the exact height of a pipeline above the sand, and the volumetric shape of a shipwreck's boiler, effectively allowing us to drain the water and look at the object as if it were sitting on a table in a lab. The limitation of the ping rate is a fundamental constraint imposed by the speed of sound in water, dictating the maximum speed at which a survey ship can travel. Sound travels at roughly 1,500 meters per second. To measure the depth, the sonar must send a pulse and wait for it to return before sending the next one. In deep water, say 5,000 meters, the round trip takes nearly 7 seconds. During those 7 seconds, the ship is moving. If the ship moves too fast, there will be gaps in the coverage along the track, a phenomenon known as holiday. To ensure 100% coverage, the ship must move slowly enough that the footprint of the next ping overlaps with the previous one. In the deepest trenches, survey ships must crawl at a walking pace to maintain data density. This speed of sound barrier means that we cannot simply speed up the mapping of the ocean by building faster boats. We are limited by the physics of the medium itself. We have to wait for the ocean to answer, and the ocean takes its time. The acoustic phenomenon of multipath interference in shallow water creates a hall of mirrors that can confuse even the most advanced sonar systems. When mapping in a harbor or a shallow channel, the sound pulse doesn't just go down to the bottom and come back. It bounces off the bottom, hits the surface, bounces back to the bottom, and then returns to the transducer. It can also bounce off the keel of the ship, a nearby breakwater, or the hull of a docked tanker. The sonar receiver hears a chaotic cacophony of echoes, the true echo followed by a series of ghost echoes that arrive milliseconds later. These ghosts can appear as false seafloors or jagged artifacts on the screen. The computer must use sophisticated algorithms to identify the first arrival, the true bottom, and discard the reverberations. It is like trying to have a conversation in a tiled bathroom where your own voice echoes endlessly. The sonar must filter out the noise of the room to hear the single clear note of the depth. The mapping of the exclusive economic zone, EEZ, is the single largest driver of hydrographic survey work in the 21st century, transforming oceanography into a tool of geopolitical expansion. Under the United Nations Convention on the Law of the Sea, UNCLOS, a coastal nation can claim sovereign rights over the seabed resources up to 200 nautical miles from its shore. However, Article 76 allows nations to extend this claim even further, up to 350 miles or more, if they can prove that the geology of the continental shelf extends beyond the 200-mile limit. This requires high-resolution sonar data. Nations are racing to map the foot of the slope and the thickness of the sediment layers in the deep abyss. They are looking for the exact point where the continental crust ends and the oceanic crust begins. This mapping is not for science, it is for ownership. A single line of sonar data defining the edge of the shelf can secure billions of dollars in oil, gas, and mineral rights. The survey ships patrolling the Atlantic and Arctic margins are drawing the new borders of the world, using sound waves to claim territory that no human will ever walk on. The integration of magnetometers with sonar surveys adds a sixth sense to the search for shipwrecks, allowing us to see metal that is buried or camouflaged. While sonar detects shapes on the surface of the seabed, a magnetometer detects anomalies in the Earth's magnetic field caused by ferrous objects. Iron anchors, steel hulls, and cannons distort the local magnetic field. A towfish equipped with a magnetometer flies over the seabed like a metal detector. It can spot a shipwreck that has completely collapsed and been buried by sand, invisible to the sonar. It can distinguish between a rock formation, which is non-magnetic, and a pile of cannonballs, which is magnetic. The data appears as a dipole signature on the chart, a spike of positive and negative magnetic intensity. By overlaying the magnetic map on the sonar map, archaeologists can confirm that a bump in the mud is indeed a man-made object, seeing the invisible magnetic aura of the iron resting in the dark. The acoustic interference caused by biological noise, specifically the snapping shrimp layer, creates a permanent crackling noise floor in tropical waters that sonar operators must punch through. Snapping shrimp live in massive colonies on coral reefs and rocky bottoms. They snap their claws to stun prey, creating a cavitation bubble that collapses with a loud pop. When billions of shrimp do this simultaneously, it creates a background roar that sounds like frying bacon or static. This noise covers a wide frequency spectrum, often overlapping with the frequencies used by high-resolution sonar. In shallow tropical waters, this biologic clutter can mask the return signal from the seabed, reducing the range of the sonar. The ocean is not silent, it is screaming. The surveyor must increase the power of the ping to shout louder than the shrimp, engaging in a contest of decibels with the tiny crustaceans that own the acoustic landscape of the reef. The thermocline acts as a treacherous acoustic mirror that can hide submarines and distort bottom maps by bending sound waves violently. The thermocline is the boundary layer where the warm, sun-heated surface water meets the cold, deep water. The change in temperature causes a sharp change in the speed of sound. When a sonar beam hits this layer at a shallow angle, it can reflect off it entirely, bouncing back up to the surface without ever touching the bottom. This creates a shadow zone below the layer where the sonar cannot see. Submarines deliberately hide in this shadow zone to avoid detection. For mappers, the thermocline is a lens that refracts the beams, causing the seafloor to appear deeper or shallower than it is. If the sound velocity profile is not measured perfectly with a CTD probe, the map will show a false shelf or a curve where the bottom is actually flat. The surveyor must pierce this thermal veil, accounting for the bending of the rays as they pass through the temperature gradient. The detection of submerged landscapes, such as the drowned continent of Doggerland in the North Sea, relies on the ability of low-frequency sonar to penetrate the seabed and reveal the paleo channels. During the last ice age, sea levels were lower and vast areas of the continental shelf were dry land with rivers, lakes, and hills. As the ice melted, the sea rose and buried these landscapes under meters of marine sand. Sub-bottom profilers can see through the modern sand to find the hard surfaces of the ancient land. They reveal the meandering paths of extinct rivers, the basins of filled-in lakes, and the peat beds of drowned forests. Archaeologists use this acoustic data to reconstruct the map of the Stone Age world, locating the high ground where prehistoric humans would have camped. The sonar effectively peels back the ocean to show the land as it was 10,000 years ago, a ghost geography hidden beneath the waves. The specific challenge of mapping water column anomalies allows sonar to detect not just the bottom, but the things floating above it, including gas seeps and fish schools. Modern multibeam systems can record the data from the entire water column, not just the first bottom return. This water column data is massive in volume, terabytes per day. When processed, it reveals flares of methane gas bubbling up from the sea floor, looking like towering flames in the acoustic image. It reveals the density of fish schools, allowing for biomass estimation. It can even detect the fresh water leaking from submarine springs. This technology turns the empty space on the chart into a volume of information, allowing us to see the dynamic processes of the ocean, the breathing of the crust, and the swarming of life hovering above the static terrain of the map. The datum problem is the fundamental headache of vertical measurement at sea. Where is zero? On land, we measure height from mean sea level, but at sea, the level of the water is constantly changing due to tides, waves, and atmospheric pressure. A ship measuring a depth of 50 meters at high tide is actually over a piece of ground that is only 48 meters deep at low tide. To create a seamless map, every single ping must be corrected to a common vertical datum, usually the ellipsoid, a mathematical model of the Earth, or the geoid, the gravitational equipotential surface. This requires high-precision GPS positioning that tracks the ship's vertical movement to within centimeters. The surveyor is measuring the distance from the ship to the bottom, while simultaneously measuring the distance from the ship to the center of the Earth, subtracting one from the other to get the true elevation of the sea floor. It is a game of shifting frames of reference, trying to pin down a stable number on a heaving ocean surface. Airborne LiDAR bathymetry, ALB, bridges the gap between the land and the deep sea, mapping the white ribbon of the surf zone where ships cannot safely go. A specialized aircraft flies over the coast, firing a green laser into the water. Green light penetrates water better than any other color. The laser reflects off the seafloor and returns to the aircraft. By measuring the time of flight, the system calculates the depth. This technique works in clear water up to 50 meters deep. It captures the complex topography of coral reefs, rocky headlands, and surf breaks with incredible speed. While sonar requires a boat to slowly mow the lawn, LiDAR flies over it at 150 knots. It fills the dangerous, shallow void on the charts, connecting the topographic maps of the land with the bathymetric maps of the ocean in a seamless, continuous model of the coast. The backscatter angular response is a forensic tool used to identify the composition of the seabed without taking a physical sample. Different materials reflect sound differently depending on the angle at which the sound hits them. Mud absorbs sound at steep angles, but reflects it at grazing angles. Rock reflects sound strongly at all angles. By analyzing the curve of intensity versus angle for a patch of seafloor, algorithms can classify the sediment. We can say, this is sandy mud, or this is gravel, purely based on the physics of the echo. This allows for the creation of habitat maps that cover thousands of square kilometers. We can map the extent of a scallop bed or a male coralline algae bed without dropping a camera, reading the grain size of the sand from the acoustic signature it leaves in, the reverberation of the ping. The scour monitoring around offshore wind farms and oil rigs is a critical application of high-repeat sonar surveys, tracking the erosion caused by currents swirling around man-made structures. When a pylon is driven into the sandy seabed, it accelerates the water flow around its base, creating a vortex that scours away the sand. This can create massive pits, destabilizing the structure. Survey vessels periodically scan the base of these turbines with high-resolution multibeam sonar. The resulting images show the scour pits as deep, crater-like depressions. Engineers use this data to dump rock armor, huge boulders, into the pits to stop the erosion. The sonar acts as the eyes of the maintenance crew, watching the dynamic interaction between the steel of the industry and the fluid mechanics of the tide, ensuring that the infrastructure of the energy transition doesn't topple into the holes it dug for itself. The search for the submarine H.L. Hunley or the USS Monitor involved the use of a parametric sonar, a highly specialized tool that generates a narrow, low-frequency beam capable of penetrating deep into the sediment with high resolution. Parametric sonar exploits the non-linear interaction of two high-frequency sound waves to generate a low-frequency difference wave. This virtual low-frequency beam has no side lobes. It is a laser-like pencil of sound. It can find a buried object, like a Civil War submarine, hidden under 10 feet of mud with pinpoint accuracy. It doesn't just see the bottom, it sees the iron cylinder sleeping inside the bottom. This technology allows us to find the history that has been swallowed by the sedimentation of the continental shelf, locating the metal bones of the past that have been erased from the visible world. The acoustic signature of a methane seep looks like a flare on the sonar screen, a vertical column of noise rising from the bottom. These gas bubbles scatter sound strongly. Mapping these flares is crucial for climate science, as methane is a potent greenhouse gas. But it is also critical for understanding submarine slope stability. Methane hydrates, frozen gas within the sediment, can melt and destabilize the slope, causing massive underwater landslides and tsunamis. Sonar surveys look for the pockmarks on the seafloor, where gas has exploded out in the past. These craters can be hundreds of meters wide. The sonar reveals a seafloor that is bubbling and burping, a porous skin that leaks hydrocarbons from the deep reservoirs, posing a hazard to oil platforms and a variable in the climate equation. The waterfall display is the real-time visual interface that sonar operators stare at for hours, a scrolling image that paints the seafloor line by line. As the ship moves, new data appears at the top of the screen and scrolls down, looking like a continuous waterfall of texture. The operator watches for the telltale shapes of wrecks, rocks, or pipelines. A shipwreck appears as a sudden, bright geometric shape followed by a long, dark acoustic shadow. The operator must instantly recognize this anomaly and mark the coordinates. It is a hypnotic, scrolling vigil. The colors are usually false color scales, gold for high intensity, blue for low. The operator is interpreting a soundscape translated into a rolling image, searching for the hard edges of humanity in the soft, organic noise of the seabed. The calibration of a multibeam system, known as the patch test, is a rigorous geometrical exercise that must be performed every time the equipment is modified. The ship must drive a specific pattern of lines over a distinct feature on the sea floor, like a wreck or a rock slope. It drives the same line at different speeds and headings. By comparing the overlapping data, the surveyors can calculate the tiny angular misalignments of the transducer, roll bias, pitch bias, and yaw bias. If the transducer is tilted by even a fraction of a degree, the map will be distorted, shifting mountains by meters. The patch test aligns the acoustic eyes of the ship with its navigational brain, ensuring that the sound beams are pointing exactly where the computer thinks they are. It is the calibration of the instrument, tuning the geometry of the survey to the reality of the hull. The problem of aeration, or bubbles sweep down, is the bane of sonar operations in rough weather. As the ship's bow smashes into a wave, it drives a cloud of air bubbles under the hull. These bubbles sweep back along the keel and pass over the face of the sonar transducer. Air is an acoustic insulator. It blocks sound almost perfectly. When the bubble cloud hits the sonar, the bottom signal is lost. The screen goes blank, or white. This forces survey ships to slow down or change course to reduce slamming. In heavy seas, the data becomes gappy and noisy. Engineers design bulbous bows and gondolas to push the bubbles away from the sensors, but the ocean's turbulence is a constant adversary. The surveyor is fighting for a clean column of water, a bubble-free path for the sound to travel, in an environment that is constantly churning air into the liquid. The global effort of Seabed 2030 is a collaborative project aiming to map 100% of the ocean floor by the year 2030, a goal that requires a massive scaling up of data collection. Currently, most commercial ships, cruise liners, and fishing boats run their echo sounders only for navigation, deleting the data as they go. The project encourages these vessels to install data loggers to record their depth soundings and upload them to a central database. This crowdsourced bathymetry turns every ship into a survey vessel. A cruise ship crossing the Pacific can map a strip of the abyss that no research vessel would ever visit. It is a distributed effort to fill the blank spaces on the map, aggregating the transits of the global fleet to build a complete picture of the planetary surface, proving that the solution to the vastness of the ocean is the ubiquity of human traffic. The phenomenon known as the afternoon effect is a diurnal headache for hydrographers that illustrates the exquisite sensitivity of sound to the heat of the sun. As the sun rises and beats down on the ocean's surface throughout the day, it warms the top few meters of the water column. This warming creates a sharp, negative temperature gradient near the surface. The water gets colder very quickly, just a few meters down. Because sound travels faster in warm water, the sonar beams emitted by the ship are bent downward sharply as they leave the hull. This downward refraction is known as quenching. It causes the sound energy to dive steep and deep, shortening the range of the sonar and creating a shadow zone near the surface where the ship cannot see. By the late afternoon, after hours of solar heating, the effect is strongest. The sonar map might start to curl or distort at the edges as the sound speed profile changes faster than the surveyors can measure it. To combat this, the crew must constantly dip the sound velocity probe, chasing the changing temperature of the afternoon sea, battling the sun itself to keep the acoustic lines straight in a fluid that is constantly warping under the heat of the day. The deployment of Slocum gliders represents the shift towards slow oceanography, utilizing buoyancy rather than propellers to map the ocean's properties in near silence. These yellow, torpedo-shaped robots do not have engines. Instead, they have a variable buoyancy engine, a bladder that fills with oil to make them float or empties to make them sink. They move through the ocean in a sawtooth pattern, gliding down to a kilometer deep and then gliding back up, using wings to convert vertical motion into forward motion. Because they use so little power, they can stay at sea for months, crossing entire ocean basins at the speed of a walking human. They are often equipped with CTD sensors to measure the sound speed profile of the ocean continuously. They are the silent scouts of the sonar world, drifting through the deep, collecting the temperature data that the noisy surface ships need to calibrate their maps, moving with the rhythmic breathing of their own oil bladders. Mapping the Arctic Ocean requires a complete inversion of the standard sonar orientation, turning the gaze from the bottom to the top. Submarines and AUVs operating under the ice cap use upward-looking sonar to map the underside of the ice. The ice canopy is a complex inverted landscape of keels, ridges, and valleys. Ice keels, massive blocks of ice forced downward by the pressure of colliding flows, can extend tens of meters into the water, posing a hazard to submarines. The sonar reveals this undersky as a jagged, white terrain. The sound reflects off the ice-water interface, measuring the draft of the ice with centimeter precision. This data is critical for climate science, calculating the volume of the remaining ice. The submarine navigates a tunnel between two hard surfaces, the rocky seafloor below and the icy ceiling above, pinging both simultaneously to find a safe path through the cold, dark sandwich of the polar ocean. The ping-to-chart workflow is the tedious, unglamorous back-end of ocean mapping, a digital refining process that turns raw noise into a pristine surface. When a multibeam sonar collects data, it records millions of points. Many of these are errors, bubbles under the hull, fish swimming through the beam, or acoustic interference from other ships. These artifacts appear as spikes or clouds floating above the seafloor. If left in, they would look like impossible needles of rock rising from the abyss. The data must be cleaned. Hydrographers use specialized software to visualize the soundings as a 3D point cloud. They spend hours editing the data, using digital brushes to erase the false points. It is a sculptural process, chipping away the noise to reveal the true shape of the bottom. This manual cleaning is the bottleneck of hydrography. For every hour of survey, there can be several hours of processing, a quiet vigil in front of a screen to ensure that the mountain on the map is made of rock, not a school of tuna. The discovery of the 90 East Ridge in the Indian Ocean was a monumental achievement of single-beam sonar profiling that revealed a linear scar across the planet's face. This underwater mountain range is 5,000 kilometers long, longer than the Andes, and runs almost perfectly straight along the 90th meridian east. It was formed by the Indian tectonic plate moving northward over the Kerguelen hotspot, a blowtorch in the mantle that punched a hole in the crust and built a volcano, then punched another as the plate moved, creating a track of fire that cooled into stone. The sonar profiles revealed that this ridge is not just a line, but a complex series of N-echelon blocks and seamounts. Mapping it helped confirm the speed at which India crashed into Asia to form the Himalayas. The ridge is the tracks of the subcontinent's journey, a fossilized wake of a continent's migration preserved in the basalt of the ocean floor. The dolphin effect and the subsequent mitigation protocols acknowledge the impact of high-power sonar on the sensitive hearing of marine mammals. Whales and dolphins live in an acoustic world. Sound is their sight. The loud pings of a deep-water multi-beam sonar or a seismic air gun can disturb, deafen, or even strand them. To prevent this, survey ships employ marine mammal observers, MMOs, who scan the horizon with binoculars. If a whale is spotted within a certain exclusion zone, the operations must stop. The sonar is shut down. When operations resume, they use a soft start or ramp-up procedure. The sonar begins at a very low power and slowly increases in volume over 20 minutes. This gives any animals in the area a chance to swim away before the sound reaches dangerous levels. It is a polite knock before entering the room, a protocol that attempts to balance the need to map the Earth with the right of the ocean's residents to live in peace. The deep tow systems developed by the Scripps Institution of Oceanography in the 1960s were the pioneering ancestors of modern AUVs, dragging instrument packages closer to the abyss than anyone had dared before. The deep tow fish was a massive, instrument-laden sled towed on miles of coaxial cable. It carried side-scan sonar, cameras, and magnetometers. Dragging this sled was an art form. The winch operator had to play the cable like a fishing line, letting it out to sink the fish into a trench and reeling it in to pull it over a seamount. The delay between the winch action and the fish moving could be 10 minutes or more due to the drag of the wire. It was like flying a kite on a 5-mile string in a hurricane. These systems produced the first high-resolution images of the abyssal hills and manganese nodules, proving that the deep-sea floor was not a featureless plain, but a textured, rugged landscape. Mapping the Hadal zone, the trenches deeper than 6,000 meters, requires transducers made of exotic ceramics, capable of withstanding crushing pressures without losing their piezoelectric properties. Standard sonar transducers are oil-filled to balance the pressure, but at 11,000 meters in the Challenger Deep, the pressure is so immense that even the oil compresses significantly and the ceramic crystals can crack or depole, lose their electric charge. Hadal sonar systems use pressure-compensated designs where the internal components are bathed in specialized fluids and the housing is made of titanium. The acoustic frequency must be low, usually 12 kHz, to penetrate the miles of water. The signal takes 14 seconds to go down and back. The operator sends a ping and then waits in silence for a quarter of a minute, listening for the faint echo from the bottom of the world. It is the longest conversation in mapping, a slow, rhythmic query into the ultimate dark. The acoustic signature of a black smoker hydrothermal vent is a complex mix of scattering and absorption caused by the chaotic turbulence of the superheated water. When 400 degrees Celsius water blasts out of a vent into 2 degrees seawater, it creates a violent mixing zone. The density of the hot fluid is much lower than the surrounding water. When a sonar beam hits this plume, it scatters. On a side-scan record, a vent field looks like a cloud or a fuzzy patch hovering over the hard return of the rock chimney. The bubbles of gas often released by the vents also reflect sound strongly. By tuning the sonar to look for these mid-water anomalies, prospectors can find the vents without seeing the smoke. They listen for the density disturbance, the acoustic shimmer of heat rising from the crust. Sub-bottom profiling of paleochannels reveals the ghost rivers that once flowed across the continental shelves during the ice ages. When sea levels were lower, rivers like the Hudson, the Rhine, and the Thames flowed hundreds of miles further out to reach the ocean. They cut deep valleys into the shelf. When the ice melted, the sea rose and filled these valleys with sediment, burying them completely. To a standard multibeam sonar, the seabed looks flat. But to a sub-bottom profiler, which penetrates the mud, the V-shape of the ancient river valley is clearly visible beneath the modern sand. These buried channels are hazards for offshore wind farms. The sediment is soft and unstable, and targets for archaeologists. Early humans lived along these riverbanks. The sonar acts as a time machine, stripping away the Holocene mud to reveal the Pleistocene landscape below. Slope stability analysis using sonar is a critical tool for tsunami prediction, identifying the scars of past landslides to predict future ones. The continental slope is not stable. It is a pile of loose sediment that is constantly threatening to slide into the deep basin. High-resolution bathymetry reveals the headscarps of ancient slides, crescent-shaped cliffs left behind when a chunk of the shelf fell away. It also shows tension cracks in the sediment, indicating that a block of land is slowly detaching and ready to slide. By mapping these features, geologists can identify high-risk areas. If a massive block were to slide today, it would displace water and generate a tsunami. The sonar map serves as a risk assessment chart, highlighting the precarious piles of mud that are waiting for an earthquake to release their potential energy. The calibration of backscatter intensity is an ongoing struggle to create a standardized gray scale for the ocean floor. Unlike depth, which is an absolute measurement, loudness is relative. A rocky bottom might look bright on one ship's sonar and dim on another's, depending on the power settings, the age of the transducer, and the water temperature. This makes it hard to compare maps from different years or different ships. To fix this, hydrographers are developing reference areas, patches of seafloor that are stable and well understood. Ships go to these patches to calibrate their backscatter, tuning their instruments until they all agree that this patch of sand is this shade of grey. It is an effort to standardize the acoustic palette, ensuring that a map made in 2024 looks the same as one made in 2030, allowing us to detect true changes in the seabed over time. water column imaging has transformed sonar from a tool for finding the bottom into a tool for weighing the life in the ocean. By analyzing the echoes that return from mid-water, scientists can estimate the biomass of fish stocks. A school of herring looks like a dense red ball on the sonar screen. The strength of the echo is proportional to the number of fish and the size of their swim bladders. Multibeam systems can slice through a school of fish, creating a 3D model of the shoal's shape and volume. This acoustic trawling allows fisheries managers to count fish without catching them. It reveals the massive shifting clouds of biology that drift over the static geology, adding a layer of living data to the bathymetric chart. The seamless integration of bathymetric LiDAR and multibeam sonar is required to map the white ribbon, the dangerous surf zone where waves break and ships cannot go. LiDAR uses a green laser fired from an aircraft to penetrate the water and measure depth in the shallows. Sonar uses sound from a boat to measure the deep. The two datasets must overlap perfectly to create a continuous model from the mountaintop to the ocean trench. Merging these datasets is difficult. They use different physics and different reference frames. The white ribbon is the most dynamic part of the coast, constantly changing with the tides and storms. Capturing it requires a coordinated assault from the air and the sea, stitching together light and sound to close the gap where the land meets the ocean. The snippets data format is a high-fidelity way of recording backscatter that preserves the fine texture of the seafloor within each sonar beam. In standard backscatter, the sonar records one intensity value per beam, an average. In snippets mode, the sonar records a short time series of the echo intensity within the beam's footprint. This effectively breaks the single beam footprint into dozens of smaller pixels. It improves the resolution of the backscatter image by a factor of 10. It allows the operator to see the texture of the sediment, ripples, pockmarks, at a scale smaller than the depth measurement itself. It is like zooming in on a digital photo to see the grain. Snippets allow us to see the grain of the seabed, revealing the subtle roughness that defines the habitat for crabs and flatfish. The acoustic shadow zone is a phenomenon where sound waves are bent away from a target, making it invisible, a concept critical in both mapping and submarine warfare. Because sound bends towards areas of slower velocity, it can curve downwards or upwards, leaving a gap in the middle where sound never reaches. If a seamount or a shipwreck lies in this shadow zone, the sonar will not detect it. It is effectively cloaked by the physics of refraction. Mappers must use ray tracing software to predict where these shadow zones will occur based on the current temperature profile of the water. They adjust the ship's position or the angle of the sonar beams to illuminate the shadows. It is a game of angles, trying to shine a light into the blind spots created by the bending of the rays. The use of a scatterometer exploits the relationship between sound reflection and surface roughness to measure wind speed. When the wind blows, it creates waves. Rough water scatters sound and radar in all directions, while calm water reflects it like a mirror. By measuring the backscatter from the ocean surface, satellites and sonar systems can infer the wind speed and direction. A loud, messy return from the surface means high winds and big waves. A quiet, specular return means a calm sea. This turns the surface of the ocean into a global anemometer. While usually done with radar, upward-looking sonar from AUVs can also measure this, linking the acoustic texture of the surface to the weather patterns of the atmosphere. Multi-frequency sonar systems, which transmit pulses at several different frequencies simultaneously, e.g. 100 kHz, 200 kHz, and 400 kHz, allow scientists to see the seabed in acoustic color. Different frequencies interact with the sediment differently. High frequencies reflect off the very surface of the sand. Low frequencies penetrate slightly deeper into the subsurface. By comparing the response at different frequencies, researchers can tease out more details about the sediment composition. It is similar to how our eyes use red, green, and blue light to perceive color. A multi-frequency map might show a patch of seabed that looks smooth at 100 kHz, but rough at 400 kHz, indicating a specific type of gravel or shell hash. This technology is moving us from black and white mapping to full-spectrum acoustic characterization. The swath width limitation in deep water is a geometrical constraint that frustrates the desire for speed. As the water gets deeper, the sonar fan spreads out. However, the outer beams, those at the edges of the fan, have to travel a very long distance through the water at a shallow angle. They are subject to more attenuation and refraction errors. The data at the edges of the swath becomes noisy and unreliable. To maintain high quality, hydrographers often have to narrow the swath angle in deep water, throwing away the outer beams. This means the road they are paving gets narrower the deeper they go. Mapping the abyss is therefore slower than mapping the shelf, not just because of the travel time of sound, but because the usable flashlight beam becomes tighter relative to the vastness of the darkness. The sheer human effort of caris cleaning, referring to a popular hydrographic software, is the unsung labor of the industry. After the ship returns to port, teams of data processors sit in dark rooms for months. They load the terabytes of raw sonar data. They look at the point clouds from every angle. They manually flag noise points that the automatic filters missed. They check the connection between adjacent survey lines to ensure they match. If the tide correction was wrong, the lines won't line up, creating a washboard effect that must be fixed. This manual polishing is what turns a messy scientific data set into a navigational chart that a captain can trust with their life. It is a digital sculpture process, a slow, meticulous smoothing of the virtual Earth that requires infinite patience and a keen eye for the difference between a rock and a glitch. The detection of polymetallic nodules on the abyssal plains is a specific application of backscatter analysis that turns the survey ship into a prospector for the batteries of the future. These potato-sized lumps of manganese, nickel, and cobalt sit loosely on the deep sediment of the Clarion-Clipperton Zone in the Pacific. To a standard depth sounder, the abyssal plain looks flat. But to a backscatter system, the nodules shine. They are hard objects resting on soft mud. A high-intensity return from a flat area indicates a pavement of these valuable rocks. Mining companies use this data to map the density of the fields. They look for the specific acoustic texture of a nodule carpet. The sonar reveals the distribution of this slow-growing resource, formed over millions of years by the precipitation of metals from the seawater. It is a treasure map drawn in sound intensity, guiding the controversial dredging machines toward the densest concentrations of metal that lie waiting in the eternal dark. The concept of acoustic daylight, or ambient noise. Imaging proposes a radical shift from active to passive sonar, using the natural noise of the ocean to see. Traditional sonar is like using a flashlight in a dark room. You send a ping and see the reflection. Acoustic daylight is like taking a photograph using the existing light in the room. The ocean is noisy, waves breaking, rain falling, shrimp snapping. This background noise illuminates objects. A silent submarine or a rock reflects this ambient noise. By using a sophisticated acoustic lens, a dish lined with hydrophones, a camera can form an image based on how objects scatter the background sound. It allows us to see a target without ever emitting a ping, maintaining total silence. It exploits the chaotic energy of the ocean itself, turning the roar of the surf into a source of illumination for the silent observer. The mapping of the subglacial cavities beneath the Antarctic ice shelves, such as the Thwaites Glacier, is one of the most high-stakes sonar missions on Earth, requiring robots to swim into a freezing, crushing tunnel. We need to know how warm water is melting the ice from below. AUVs, like RAN, are deployed to swim under the floating ice shelf. They use upward-looking sonar to map the ceiling of ice and downward-looking sonar to map the seabed. They reveal a landscape of inverted canyons and terraces in the ice, carved by the turbulent flow of warm water. The sonar data shows the grounding line, the exact point where the glacier lifts off the bedrock and begins to float. This line is retreating. The map produced is a diagnostic chart of a dying glacier, a geometry of melt that determines the future sea level of the entire planet, captured by a lonely robot navigating the blackest, coldest water on Earth. The forensic analysis of scour marks left by iceberg keels on the seafloor provides a paleoclimate record that is read like braille by the sonar. When an iceberg runs aground, it plows a furrow in the mud. These furrows can cross each other, creating a chaotic palimpsest of scratches. By mapping the depth and orientation of these ancient scours on the continental shelf, scientists can determine the size of the icebergs that existed during the last ice age. A deep scour means a massive iceberg, which implies a massive ice sheet carving it. The orientation tells us the direction of the ancient currents and winds. The sonar reads the history of the ice written in the mud, decoding the movements of frozen giants that melted 10,000 years ago, but left their tracks carved into the continental margin. The phenomenon of brine pools in the Gulf of Mexico creates an acoustic interface so sharp it looks like a false bottom or a lake within an ocean. These pools are depressions filled with hypersaline water that is much denser than the surrounding seawater. The boundary between the normal seawater and the brine is distinct. When a sonar pulse hits this interface, it reflects. On the screen, it looks like a flat, solid surface hovering in a crater. It is only when the submersible goes down that the truth is revealed. It is a liquid lake underwater. The sonar detects the difference in density. These pools are toxic to most life, but often ringed by mussels and tube worms living on the chemosynthetic energy at the shoreline. The sonar finds these underwater lakes by listening for the echo of the salt, mapping the geography of fluids that refuse to mix. The strategic routing of submarine communication cables relies entirely on high-resolution bathymetry to find a safe path through the hazardous terrain of the abyss. The internet travels through fiber optic cables about the thickness of a garden hose resting on the seafloor. If a cable is laid over a sharp rock ridge, the currents will rub it back and forth until it snaps, a chafe break. If it is laid on a steep slope, a landslide will sever it. Survey ships spend months mapping a fairway, a safe corridor of flat, stable sediment. They look for choke points between seamounts and avoid the chaotic terrain of fracture zones. The resulting map is a highway for data. Every email and video stream travels along a path that was carefully chosen by a hydrographer staring at a sonar screen, threading a glass needle through the mountain ranges of the deep. The bistatic sonar configuration separates the transmitter from the receiver, placing them on different platforms to defeat the stealth technology of submarines. Modern submarines are coated in anechoic tiles that absorb sonar pings, making them invisible to a monostatic sonar, where the transmitter and receiver are in the same place. However, these tiles often scatter sound in other directions. In a bistatic system, one ship emits the ping, and a second ship, or a buoy miles away, listens for the echo. The geometry of the reflection is different. The stealth coating might hide the sub from the pinger, but it inadvertently reflects energy toward the listener. This cooperative geometry turns the ocean into a trap. It requires precise timing synchronization between the two platforms. It is a game of acoustic triangulation, catching the shadow of the silent hunter by listening from an unexpected angle. The preservation of the sonar data itself faces the challenge of digital rot, requiring active curation to ensure the maps of today are readable in the future. A raw sonar file is a complex binary package containing time, position, attitude, and acoustic intensity data. The file formats change over time. Old data from the 1980s is stored on magnetic tapes that are degrading. Hydrographic offices are engaged in a massive data rescue effort, migrating these petabytes of soundings onto modern servers. A map is only useful if you can open the file. The history of the ocean floor is stored in server farms, vulnerable to bit rot and format obsolescence. The archivists of the deep are fighting entropy in the digital realm, ensuring that the hard-won depth soundings of the past century do not vanish into the digital void. The acoustic void of gassy sediments creates a blank spot on the map where the sound simply dies. In areas with high organic content, like river deltas, the mud is filled with microscopic bubbles of methane and carbon dioxide from decaying matter. These bubbles scatter and absorb sound energy so effectively that the sonar cannot penetrate them. The sub-bottom profiler shows a wipeout zone, a white blank space beneath the seabed surface. We cannot see the bedrock below. This acoustic turbidity hides geological hazards like faults or buried channels. It is a frustrating veil. The surveyor knows the geology continues, but the gas creates a fog that no frequency can pierce, a blind spot generated by the biology of decay. The Deep Ocean Assessment and Reporting of Tsunamis, DART, system relies on acoustic communication between a seafloor sensor and a surface buoy to warn the world of approaching waves. A pressure sensor sits on the bottom, measuring the weight of the water column to the millimeter. When a tsunami wave passes overhead, the pressure spikes. The sensor converts this data into a coded series of sound pulses, an acoustic modem. It transmits these pulses up through kilometers of water to the buoy on the surface, which then relays the warning via satellite. This acoustic link is the lifeline of the system. It must work in the violent noise of a storm and the silence of the deep. It is a conversation between the crust and the atmosphere, a warning shout carried on a sound wave that races ahead of the disaster. The discovery of asphalt volcanoes in the Gulf of Mexico was a surreal moment where sonar identified structures that looked like lava flows but were made of tar. These features, such as the Chapapoytenols, show flow patterns similar to basalt volcanoes. The sonar backscatter showed a hard, reflective surface. When visited, they were found to be eruptions of heavy bitumen, asphalt, that had squeezed out of the seafloor and flowed downhill before hardening. They are colonized by worms and crabs. The sonar map revealed the viscosity of the Earth. It showed us that the seafloor can bleed oil that solidifies into rock-like formations. It is a landscape of frozen tar, mapped by the hardness of the hydrocarbons. The calibration of the mounting angle of the sonar transducer is a geometry problem that involves the dry docking of the ship. The transducer must be aligned perfectly with the keel. A surveyor uses a laser total station, a surveying tool used on land, to measure the exact position of the transducer relative to the ship's GPS antennas while the ship is out of the water. This dimensional control survey measures the distances to the millimeter. These offsets are entered into the sonar computer. If the measurement is off by a centimeter, the depth will be wrong by meters in the deep ocean. It is the physical alignment of the machine, a terrestrial survey of the ship's hull, required to ensure the celestial navigation of the acoustic beams is accurate. The sound velocity profile, SVP, of the ocean is changing due to climate change, which introduces a subtle, creeping error into long-term mapping projects. As the ocean warms and becomes fresher due to ice melt, the speed of sound changes. A map made in 1990, using the average sound speed of that time, might be slightly different from a map made today if the water column properties have shifted. Hydrographers track the heat content of the ocean through the speed of sound. The ocean is an acoustic thermometer. By measuring how long a sound pulse takes to travel across an ocean basin, acoustic tomography, scientists can measure the average temperature of the entire ocean. The map is not static. It breathes with the climate. The phantom shipwrecks, appearing on low-resolution sonar, are often actually geological features that trick the eye with their geometry. A rectangular rock formation or a straight-edged dike can look exactly like a ship on a side-scan record. These geologic fakes entice treasure hunters and archaeologists. It requires a closer look, often with a magnetometer or a higher frequency pass, to distinguish nature's straight lines from humanity's. The ocean floor is capable of mimicry. It produces shapes that trigger our pattern recognition, forcing us to verify the target with the unblinking eye of the magnetic sensor. The far-field effect in sonar transmission refers to the distance from the transducer where the sound wave stabilizes into a coherent beam. Close to the face of the transducer, the near field, the sound pressure is chaotic and fluctuating. You cannot map in the near field. This physics limitation means there is a minimum depth for every sonar. A deep water system cannot map the water right under the hull. It needs room for the beam to form. It is like trying to read a book with the page pressed against your eyeball. The sonar needs a bit of distance to focus, creating a blind skin of water right next to the ship that must be ignored. The search for the black boxes of crashed aircraft, such as Air France 447, relies on a specific passive sonar listening for a pinger. The flight recorders are equipped with an acoustic beacon that emits a pulse at 37.5 kits once per second. This is a high-frequency sound that does not travel far, maybe 2 to 3 kilometers. To hear it, the searchers must tow a pinger locator deep near the bottom. They drag a listening ear through the mountains of the abyss, waiting for the rhythmic ping, ping, ping that signals the location of the data. It is a search for a heartbeat in a graveyard, a high-frequency needle in a low-frequency haystack. The pixelization of the seafloor is the ultimate product of the survey, transforming the analog reality of mud and rock into a digital grid. The ocean floor is divided into square cells. In deep water, a cell might be 50 meters by 50 meters. In shallow water, 1 meter by 1 meter. The computer assigns a single depth value to that cell. We do not see the infinite variability of the sand grains. We see the average. The map is a digital abstraction, a model made of millions of tiny squares. As technology improves, the squares get smaller, and the picture gets sharper. But we are always looking at a grid, a mathematical approximation of the organic curve of the Earth. The psychological impact of the featureless plane on the sonar operator is a unique form of maritime boredom, known as the blue days. For days, the ship might steam over the abyssal plain. The sonar screen shows a flat line. Nothing changes. The waterfall display is a monotonous curtain of blue. The operator must remain vigilant for the sudden appearance of a seamount or an anomaly. But the sheer vastness of the empty ocean is hypnotic. It is a reminder of the scale of the planet. Most of the Earth is not dramatic canyons or mountains. It is vast, flat, muddy plains that stretch for thousands of miles, a silence on the map that must be verified mile by mile. The first return versus the second return in LiDAR bathymetry allows for the mapping of the seabed even under a canopy of kelp. The laser pulse hits the kelp floating on the surface. The first return. Some of the light punches through the gaps in the leaves, travels to the bottom, reflects, and returns. The second return. The system records both. By filtering out the first returns, the hydrographer can defoliate the ocean, digitally removing the kelp forest to reveal the rock beneath. This technology allows us to see the bare earth in the most cluttered, vegetated environments of the coast, stripping away the biology to measure the geology. And finally, we confront the reality that despite our terabytes of data and our fleets of robot ships, the ocean remains largely a mystery of volume. We map the skin, the interface between the water and the rock. But the volume of the water itself, the dark, pressure-filled space where the squids migrate and the whales sing, is a dynamic, shifting ghost that resists mapping. The sonar beam passes through it to find the bottom, treating the water as an obstacle to be corrected for. Yet, it is the water that holds the life. Our maps are empty stages, waiting for the actors. We have built the floor plan of the theatre, but the play is happening in the dark, in the water column that we largely ignore. The acoustic map is a triumph of human persistence, a candle lit in a cathedral of infinite darkness, revealing the shape of the room, but leaving the air filled with shadows. As the ping fades into the distance and the waterfall display scrolls to a halt, the image of the seafloor remains burned into the digital memory. A landscape of mountains that no eye has seen, painted in the colors of sound. The ship moves on, leaving a swath of knowledge in its wake, a paved road of data in the wilderness of the deep. The ocean is heavy, deep, and silent, but we have learned to listen to its shape. If you enjoyed this voyage into the acoustic depths of our planet, I invite you to leave a like, subscribe to the channel, and share your thoughts in the comments below. It helps this little submersible of curiosity find its way to other sleepy travelers. But for now, let the current carry you. Let the deep water hold you. You are safe. You are drifting. Good night.